So actually, we talk about the inductor, and actually, inductor is something like a coil with maybe a solenoid or whatever. Actually, an inductor is to generate some magnetic field, generate some magnetic field. So how large the inductance is depends on how large the magnetic flux per unit length it can generate. So we calculate the magnetic flux and divided by the unit current and in unit length. Actually, not unit length. Actually, if you multiply small l to the right side, so the inductance is proportional to the magnetic flux is generated, and also yeah, depends on how dense the coil can be. So if this n is larger, it is inverse to the square of this small n. Actually, it's normalized by the current. Normalized by the current. So if two coils which we can now call inductors are near each other, the current I in one coil produces a magnetic flux phi b through the second coil. We have seen that if we change this flux by changing the current, and induced EMF appear in the second coil according to the Faraday's law, just like what we have mentioned in the previous 2 or 3 slides in this chapter. So according to Faraday, induced EMF appear in the first coil as well. So this process is called self-induction. So it mentioned a little bit more because as long as you have two coils, you have one and another one. So suppose there are some current going into the loop, and of course this one will generate magnetic field. So there will be net flux, or suppose this is changing, or maybe this is a constant current and you move this one close to another one, so that the magnetic flux for this inductor is changing. So there will be EMF. And as long as there are EMF, there will be some current. Which means that it will also generate some sort of magnetic field. And this one will make the magnetic flux for this coil changing. So this one influences the magnetic flux for this one. So there will be EMF, and this EMF will generate magnetic field. And this magnetic field will change the magnetic flux for the original coil. So that this one influences that one, and will generate another EMF for this one. And this is called the self-induction. Or maybe it doesn't necessarily like that. For a single coil, for a single inductor, even for a single inductor, we have current, so that this loop will generate the B field, and this B field will make the magnetic flux for another coil changing, maybe this coil, and then changing the magnetic flux for this coil, and this one will generate another magnetic flux. Cancel part of it, or maybe cancel part of the changing to be more precise. So it obeys the Faraday's law of induction just as other induced EMF do. Thus, in any inductor such as coil, solenoid, or toroid, self-induced EMF appear whenever the current changes with time. Yeah, so it would be somehow like this. We can quantify it with the magnetic flux equals L times the I. L times the I. Suppose this I is a constant. And according to the Faraday's law, EL is this one. EL is this one. Is the time derivative of the magnetic flux So we just need to take the derivative for this equation on both sides, and then we have another minus sign. So that this term can replace the left-hand side, so that we have the electromotive force for the inductor equals negative L di dt. And actually, in circuit analysis, you should have learned the equation as VL equals L di dt. That's why yesterday I mentioned that in a circuit point of view, sometimes you can imagine V is negative EL. Because from a circuit point of view, we consider VL is the voltage drop for the inductor, and EL here means it acts like a voltage source or a battery-like element. So they should have a negative sign in between. So an induced EMF EL appears in any coil in which the current is changing. So as long as the current is DC current, then there will be no voltage drop. And actually, as you have learned in the circuit analysis, you know the impedance of the inductor is J omega L, and suppose omega is 0, then the impedance is 0, so there will be no voltage drop for DC. Okay. So next one, we talk about the RL circuit. RL circuit is somehow like this. If a constant EMF is introduced in a single loop circuit containing a resistance R and an inductance L, so the current will be like this, and inductive time constant. So actually, so just in case you forgot, it is somehow like this. We use the KVL for this one. So for the right hand side, we have E, and this one we have IR. R times I is the voltage drop, the Ohm's law for the resistance. And for this one, we have L di dt. So actually, somehow this is R, this is L. So yeah, and this is L, and this is I. So this side is the voltage drop for the R and VR. V out is actually I times R, and this one VL actually L di dt. And according to the KVL, we have E equals VR plus VL. Actually, last semester I find the civil engineering student very hard to understand this kind of stuff. Okay, so to solve this constant coefficient ODE, we just maybe we first divide L, so that it becomes something like this. So in order to solve this one, we let I equals to A exponential to maybe we only need to make it I exponential to ST, and then you substitute here, and then take the derivative. S will come out, so we have S exponential to ST plus RL exponential to ST equals. First of all, we solve the right hand side to be zero. So this one can be cancelled. So we know that S equals to minus R over L. So that the homogeneous solution is A exponential to minus RL times T. So this is the homogeneous solution for the other natural, not natural. This is the homogeneous solution, and the particular solution. This one is a DC, so that I should be another DC. So maybe we let I equals to B, and then substitute it here and take the derivative. It becomes zero. So left hand side R over L times B, and then equals to E over L. So B would be E over L times L over R. So L cancel, so it becomes E over R. And in that case, this is the particular solution. So the overall I should be the I homogeneous solution plus the particular solution, which is A exponential to minus R over LT plus E over R. And for the initial condition, I should be zero. Yeah, I should be zero. I0 plus should be zero. I0 plus should be zero. So which means that 0 equals this one should be 1, t equals to 1, exponential to 0 should be 1, so this is A plus E over R, so that A equals negative E over R, and it turns out that it will become, so this one I would be E over R, 1 minus like this. This is I like that, and this tau L is L over R, and put it in the denominator. So we have R over L here, which is actually the same. And it mentioned that I is this one. So for another state, which means that suppose you turn it on, and then the I will suppose you turn it on, then there will be a current, there will be a voltage here, and then and the inductor will somehow like the short circuit, there will be no voltage drop, but there will be a current, which is actually E over R, because as t tends to infinity, this term will be 0. So I will be E over R. And suppose to turn it off, then it will exponentially decay. So actually, for that case, you solve a similar one, but okay, you remove this one by a 0, and then you repeat the whole process, and then you find that, oh, we don't have this one, and we find that I0 plus should be E over R, which is the final value for these cases, which should be equal to A exponential to minus A, should be times 1, because we substitute 0 here, so that A times 1, which is A. So finally, for that case, we know that I should be E over R exponential to minus R over LT, which is this one. So here we have an example problem. So the figure figure A shows a circuit that contains 3 identical resistors. So 3 resistors with a resistor 9 ohm, 2 identical inductor with inductance L equals to 2 millihenry. 2 millihenry. This is L, this is L. And E equals to 18 volt. 18 volt. What is the current I through the battery just after the switch is closed? Okay, so maybe let me go back a bit. So it tells you that, well, so for easy, then you can just ignore it. But actually, for an inductor, and if it is a DC source, then for the steady state, the inductor will just somehow like a short circuit, but not for the transient response. Only for the steady state, the inductor will look like a short circuit. And for a capacitor, it looks like an open circuit. So, so what is the current I through the battery? After the switch is closed. So at the very beginning, and another concept you need to remember is that the current of the inductor is continuous. The current of the inductor is continuous. So L for inductor continuous is the current. For capacitor, the continuous variable is V, and for steady state, so the inductor is just like a short circuit, well, just like an arc. So for the capacitor, it should be an open circuit. This is a little bit you may need to keep in mind. So for this one, it is actually very simple, because for the initial state, there should be no current. So just after the switch is closed, there should still be no current going through this path and that path, which means that I should be nothing but E over R, which is 18 over 9, which is 2A. Any questions? Be very easy, right? So what is the current through the battery after after the switch has been closed for a long time? A long time means this one is a short circuit, this one is a short circuit, which means that we have three resistance parallel with each other. So R parallel R is nothing but R over 3. So actually, I should be E over R over 3, something like that, which is 18, and here it is 9 over 3. 9 over 3 is 3, so which is 6A. So very easy also. Any questions? No questions. Okay, so solenoid has an inductance of 53 millihenry. 53 millihenry, and resistance 0.37 ohm. If the solenoid is connected to a battery, how long will the current take to reach half of its final equilibrium? Okay, so actually for this one, we should know that tau L, which is L over R, the time constant for an inductor, which is 53 milli times 10 to minus 3, and then over 0.37, which is 143.2 millisecond. And suppose the VL should be somehow like the E over L times 1 minus, and let me write it out. So there should be a term like that, like this. So actually we can just make the condition like this, because actually we can write the whole stuff. It is VE over L times this, and then E over L like this, because it mentioned that it reached half of its final equilibrium, which means that the final equilibrium is E over L, and final should be and this point should be 0.5 E over L, but actually we don't need this stuff. They can be cancelled, so finally it should be like that. And we find out that T should be tau L ln2, because we just move this to the right hand side, move this to the left hand side. So left hand side to be 1 minus 0.5, which is 0.5. And then the right hand side exponential 2 minus T over tau L. So we take the inverse on both sides, so it becomes 2 equals exponential to T over tau L without the minus sign here. And then we take log on both sides, so the left side will be log 2, and then the right side will be T over tau L. So finally we know that T equals tau L over times log 2, natural log of 2. So in this case, we have 132 milliseconds time ln2, which is around 0.1 second. 0.1 second. Any questions? No questions. Very simple, right? So next, we consider energy stored in a magnetic field. If an inductor L carry a current I, the inductor's magnetic field store an energy given by 1/2 Li square. So for capacitor, it has a similar equation for capacitor. UE should be 1/2 CV squared. So just mention that I is the continuous variable for inductor. V is the continuous variable for capacitor. So here we have 1/2 CV squared for the energy stored in a capacitor, and here we have 1/2 Li squared for the energy stored in an inductor. So the derivation is similar. So we have a dUB, which is P times IV. So we have and actually V is L didt. And well, so the UB should be the integration of this one. We can put, yeah. So we can change dUB to be this term, and then dt can be cancelled by the chain rule. So actually it's nothing but integrate IL dl, which is a first order polynomial. So it becomes 1/2 I squared. Maybe we should put a prime here, so that this one and this dummy variable do not repeat each other. So finally, it comes out a 1/2 Li squared. But actually, we seldom use that one. Yeah. So another sample problem. A solenoid have an inductance. Yeah, 53 millihenry and a resistance of 0.35 ohm. If a 12-volt EMF is applied across the coil, how much energy is stored in the magnetic field after the current has built up its equilibrium value? How much energy? Yeah. So for the steady state, the I0 should be E over R, which is 12 over 0.35, which means that I should be 34.38. And actually UB should be 1/2 Li squared, so which is 1/2 53 times 10 to minus 3, and then the 34.3 squared, so which gives an answer to be 31 joule. So it's very simple. It just asks you about the magnetic field after it goes to the equilibrium state, and the equilibrium state is nothing but E over R, and then you substitute L and I into the simple formula, 1/2 Li squared. So for B, after how many time constant with half this equilibrium energy be stored in the magnetic field? So for half of the energy, which means half half will be 1/2 times 1/2 Li squared half equals 1/2 Li squared. Maybe I0. It should be I0. Okay, so 1/2 can be cancelled. This one can be cancelled. L can be cancelled. So we know that I have no. This 1/2 should be on the other side. This 1/2 should be on the other side. We want to know that. So this one should be here. This 1/2 should be here, because we want to know the I have where the stored energy is half of the total energy. So which means that I have should be I0 over square root of 2. I0 over square root of 2. And actually I equals to I0 1 minus exponential to minus t over tau L. And now we want to know t prime, maybe t prime equals to I0 over square root of 2. And then actually we can solve it out. So with some sort of algebraic calculation, we know that t prime should be tau L times ln square root of 2 over square root of 2 minus 1. Actually, it's just some simple algebraic calculation. I did not make it out here, because you can just cancel this one, and then you just move this one to the left side, move that one to the right side, and then take the log, and then just repeat some simple calculation. And then you substitute tau L to be this one, 143 milli. And it turns out this one to be 176 millisecond. Any questions? So here we talk about the energy stored in a magnetic field again, but here consider a length L near the middle of the long solenoid of cross-section area A, carrying current I. The volume of the associated with this length is A times L. The area times the length is the volume. The energy UB stored by the length L of the solenoid must lie entirely within this volume because the magnetic field outside such a column is approximately zero. Moreover, the stored energy must be uniformly distributed. So it just makes some assumption that, okay, all the energy are stored inside the inductor, inside the solenoid, and they're uniform. The B field are uniform, so that the energy stored there are also uniform. In that case, we know the energy density stored there should be the total energy divided by the volume. So nothing special. So UV is Li squared over 2, and the volume is Al. So we have something like this, and then we just collect inductor over the length here, and then we have I squared over 2A. And previously, we know that L, capital L over L is this one, and the magnetic field in a solenoid is this one in the previous chapter. So that we substitute these two into here. So this one replace the first term, and then I should be B over mu naught N. So we have this one. So we have this one. So this one is this term. This one we just substitute I, and then we have this term. So we just make some simplification because n square can be cancelled. Mu zero, one of the mu zero can be cancelled. A can be cancelled. So it's just left out UB equals to a B square over 2 mu. And if you can still remember, in chapter 25, we have UE equals to 1/2 epsilon naught B squared. So I've mentioned several times that in electrostatic we have E0, and for magnetism we have 1 over mu 0, and we have E here, so that we have E here. So they are symmetric in some sense. Actually, we will see these two in chapter 33, the EM wave. We'll talk about the Poynting vector in that chapter, which is the energy propagate by an EM wave, which is related to these two stuff. Okay, so here we talk about the mutual inductance. So let's consider the figure A first. So we have a battery here. We have a resistance here. So that there will be current going like this. And in this case, this is an inductor, so it will generate some magnetic field, and this magnetic field is changing. Before it reach the steady state. So in this case, the magnetic flux of this coil will be changing. And according to the Faraday's law, this changing magnetic flux will generate an inducing EMF for the second coil. Actually, that's what I just mentioned. I just mix it up. It should be the mutual inductance, not the self-inductance is an inductance itself. Is an inductance itself. This should be the mutual inductance. So in this case, the coil one has a changing B view. This changing B view will generate a changing magnetic flux for this coil, and according to Faraday's law, this changing magnetic flux will generate an induced EMF. So an induced EMF will make this coil generate a changing B field for this coil. And this changing B field for this coil will generate changing magnetic flux for the original coil. So that it will generate another induced EMF for the first coil. And then it will loop for forever. So this is what we call the mutual inductance, rather than just I mentioned this mutual inductance. So this one generates something to influence this one, and this one generates this one. The coil one generate the B field to influence the coil two, and the coil two will generate the B field to influence the coil one back. Actually, yeah. Not necessarily that case, but here we consider that yeah, we define the mutual inductance in another way. So here we have a di1 dt, which means that the varying of I1, which will generate an induced EMF for the coil 2. So this is called a mutual inductance. For the self-inductance, it is the varying of the coil for itself, and it will change the induced EMF for itself. But here, the mutual inductance means the changing current for the first loop will generate the induced EMF for the second coil, and so as that case. So we define this. This is not the inductance anymore. We call it the mutual inductance, and we use M to represent this mutual inductance.